In this video, we introduce the three subspaces associated to a matrix, called the row space, column space, and null space. So suppose we have an M by N matrix A. So that means it has M rows and N columns. As an example, here's a 3 by 4 matrix. It's got 3 rows, 4 columns. And sometimes we can write the rows as R1, R2, all the way up to Rm. And then the columns, we can also write a matrix by its columns, C1, C2, all the way up to Cn. These are dashes, not ones. Okay. Now, the row space, what is that? Well, it's denoted row of A. Sometimes I'll not capitalize the R. And it's a vector space. And in Sage Math, here's the command to get it once you've defined a matrix A. It's simply the span of the rows of the matrix. So here are the rows, and we take the span of them. So what was span again? That just means the linear combination of those vectors. So looking at our example here, the row space of A is the span of these 3 vectors that form the rows. So the first row is 0, 1, negative 1, 2. So here we have that. Then the second row is this, and the third row is 3, 0, 0, 1. And so we just take their span. And what does that mean again? That just means the linear combination. So you take this vector and multiply it by any scalar or number, add to that this vector multiplied by any number, and add to that this vector multiplied by any number. And that will give you the vectors that arise or live in the span. So a particular vector that lies in the span is 2 times this first vector plus 1 times this second vector plus, 0 times this third vector, so I've left it off. And then we get this vector 9, 5, 2, 9 if I did the arithmetic correctly. And that's a particular vector in the row space of A. So the row space is a subspace of R to the n because each row vector has n entries, so lives inside R to the n. The column space then is similar. It's just simply the span of the columns of our matrix A, and it lives inside R to the m since each column vector has m entries, so is an element of R to the m. The column space is denoted col A, and in Sage Math the command is like so. And here's just a way of writing this. This is the linear combination of the columns. The coefficients are x1, x2, xn, are those scalars that multiply the columns. Going back to our example, here was our 3 by 4 matrix, and the columns of A, the column space of A, is the span of the columns. Here there's 4 columns, and the span again is a linear combination of these 4 vectors, and it's a subspace of R3. Sometimes we'll write the vectors as row vectors, sometimes we'll write them as column vectors. Okay, and finally the null space, denoted null of A, again sometimes I'll not capitalize the n, that doesn't make any difference, is something we've actually seen before. It's the solutions to the equation ax is equal to 0. In Sage Math, the command is a.writeKernel. There is a command a.kernel, but that will give you the left kernel, I believe. Why do we call this the right kernel? That's because we want the variable x to be on the right of the equation ax equals 0, and we want to solve for x. So again, the null space is those vectors x in R to the n such that a times x, this matrix product, is equal to 0. And if you think about what does this matrix product look like, well, if x is this column vector n by 1 column vector, and A has columns C1, C2 up to Cn, as I had on the previous slide, then A times x, when you do the matrix multiplication, is this sum here, and we want that to equal the 0 vector. So in terms of our example, here was our example, and then we want this matrix times this matrix to equal 0, and when you do the matrix multiplication, that amounts to solving a system of equations with 3 three equations corresponding to each row, and then in four variables, x1 up to x4. And that's something we started off the course with in chapter 1. So this null space is actually something we know how to compute way back in chapter 1. In this section, we'll learn how to do the following. Given a matrix A, the goal is to find a basis of its row space, a basis of its column space, and a basis of its null space. And the miraculous idea is that row reduction is all you need. By row reduction in Sage Math, the command is, if you have your matrix A, you just do A dot ref parentheses, and this will return the reduced row echelon form. This is something we've been working with throughout the entire course, the reduced row echelon form. And let's look at a simple proposition. If a matrix R is already in row echelon form, not necessarily reduced, but it could be reduced, then the following simple facts hold: that the row vectors with leading ones form a basis of the row space of R, and the column vectors with leading ones of the row vectors form a basis of the column space. Maybe I should have had column vectors corresponding to the leading ones of the row vectors. Okay, let's look at an example. The proof is actually quite simple. It just says analyze the positions of the pivot ones. Here's an example of a matrix that's in row echelon form. It's not in reduced row echelon form because above these pivots, I haven't cleared them out and replaced them with zeros. But anyway, okay, the pivots are in green. Why are they the pivots or the leading ones? That's what I'm calling them here. It's that in each row, the very first non-zero term is a 1. And so, okay, there's that 1 there. Then as we go to the second row, we go 0, 0, then we hit a 1. And then in the third row, we go 0, 0, 0, and then 1. And then the fourth row is just all zeros. So the leading ones are the pivots. Okay, and then the claim is that these rows are R1, R2, and R3, containing the leading ones or the pivots, they form a basis of the row space. And the columns containing those pivot ones, so this time it's column 1, not column 2. You do include column 3 in the basis, and you do also include column 4. So they form a basis for the column space. Just to give a slight explanation why, well, let's look at for the row space. These are the rows, the only non-zero rows. And so they definitely span the row space of R. And we need to then check that they form a basis. In other words, these rows are linearly independent. In other words, any linear combination of these first three rows, if it adds to 0, then that linear combination, each of the coefficients are 0. Okay, so if we add some number times the first row plus some number times the second row plus some number times the third row equaling 0, when we add that all up, the component in the first position would be that whatever number we multiplied the first row by times 1, which will just give back that number. The other numbers that we multiplied row 2 and row 3 by won't affect that component, the first component, because they just had zeros here. And so because we're assuming that linear combination is 0, 0, 0, 0, that forces the number we multiplied this first row by to be a 0. A similar argument will show why these columns form a basis for the column space. In this video, we defined the column space, row space, and null space. In the next few videos, we'll explain, given an actual matrix, how to find a basis for the row space, column space, and null space.